The following PhysCast deals with a non-uniform bar which is suspended and in static equilibrium. Please pause the video and read through the question carefully. So the question's asking us to compute the distance x from the left-hand side of the bar to where the bar's centre of mass is. We're given some information about the bar. Firstly, it's non-uniform, which means that its density is varying along the length. If this was a uniform bar, you would expect the centre of mass to be in the centre of the bar. That would be easy to calculate because the length of the bar is given, 6.10 metres. The bar itself is suspended by two cords which are massless, so you don't have to worry about the weight of those ropes. And we're given the angles that these two ropes make with the vertical. So one is 36.9 degrees and the other one is 53.1 degrees. We'll probably just use the angles theta and the angles phi initially. Since we're not given the mass of the bar or the tensions which are in either of these ropes, I suspect that we will have to approach this problem symbolically, and then hopefully some of those unknowns will cancel from the equations that we find. So interpreting this, it's a static equilibrium problem, so the sum of the forces is equal to 0 and the sum of the torques are also equal to 0. A couple of things that I know: I'm given the centre of mass position, which is here. Even though I don't know the mass of the bar, I can draw the weight force, mg, which is acting on the bar. It always acts through the centre of mass in a uniform gravitational field. I also know that my angle theta is less than my angle phi in this case. The way it's drawn, it's a little bit difficult to see that, but that's important because when I put the tension forces in, so there's going to be a tension force which is acting along the rope to the left, and we might call that tension T1. And when I draw the tension force which acts to the right, I know that that tension force T2 is going to be smaller. Why do I know it's smaller? Well, it has to do with the angles. If I accentuate this and say that the angle on the left hand side, theta, is small compared to the angle on the right hand side, phi, which is large, then you'll see that if I had these as my tension forces T1 and T2, the horizontal component of the tension force of T1 is much smaller than the horizontal component force of the tension force T2, the way I've drawn it. So this couldn't possibly be an equilibrium situation. I have to shrink T2 down until the horizontal component of T2 is the same as the horizontal component of T1. That's because there are no other horizontal forces on my diagram. So I've put all of the appropriate forces on my diagram acting where they are. What I now care about is a coordinate system. So let's choose x as being horizontal and y as being vertical. And I've already labelled the centre of mass point here. I think I'll use that as my pivot point for my torque calculation. The reason why I'm going to choose the centre of mass as my pivot point for my torque calculation is that the weight force mg cannot provide a torque at that point because the perpendicular distance is 0. Therefore, it will drop out of the equation, and that's good because the mass is an unknown. I don't know what that is. Right, so let's start with some evaluation. If we take the sum of the forces in the x direction for the moment, and what we're going to have to do is a little bit of trigonometry. So I want to find the component of the tension force T1 in the horizontal direction. So I can draw that in there as that dotted line. And I can get that by realizing that this angle theta here is also the angle theta in here. Remember from some geometry that if I have two parallel lines and they intersect, then those two angles are the same. That allows me to write the horizontal component of T1 as being T1 times the sine, because it's the opposite side of theta. And because x is positive to the right, then my horizontal component of T1 must be negative, because it goes to the left. The other horizontal force I have is the horizontal component of T2. Once again, this angle in here is phi, so I can write that as T2 times the sine of phi, and that's a positive quantity because it's going to the right. They're the only two components of my force which are in the horizontal direction, so they must sum to be 0. This equation might be helpful for me later on if I need to eliminate the ratio T1 over T2. So I look at the sum of the forces in the y direction, then I'm going to have in the positive y direction, I'll have T1 times now the cosine of theta, that's going to be this force going up here, plus T2 times the cosine of phi, that will be this force going up here. And then the only other vertical force will be the weight force which acts downwards, so it's negative, minus mg. The sum of those forces must be 0. Once again, this equation, I don't know the tension T1, T2, or the mass, so that might not be terribly helpful. Let's have a look at my torque equation. So the sum of the torques about the center of mass position, that's the point I'm going to choose because the torque which arises from the weight force is 0. So remembering the torque is basically equal to R crossed with F, and one way of thinking about that is it's equal to the force times the perpendicular distance, or you can think of that as being the perpendicular component of the force times the distance. So if I think about the torque which arises because of the tension in the left hand rope at T1, that's trying to turn my object in a clockwise fashion. I might call that positive, and we can see that the torque which is going to rise is just going to be my vertical component, which is T1 times the cosine of theta times by x, and then my other torque, which is caused by the tension T2, is trying to rotate it in an opposite fashion. So if going clockwise is positive, then going counterclockwise is negative, so I'll have a minus sign, and it'll be T2 times the cosine of phi is the perpendicular component of the force, and the distance from where that force acts to the point of rotation is going to be L minus x. And so the sum of those two torques is going to be 0. We want to find the distance x, so it appears only in this third equation, so we'll use this one. We will group the terms which have x in it on one side of the equation, so T1 times cosine of theta times x minus, let's see, T2 times cosine of phi times minus x makes that plus x, and I'm left with a minus T2 cosine phi times L, and so I'm going to add that to the other side, taking the terms which don't have x onto the right hand side of my equation. I can take x out as a common factor now, so I'll have x outside of T1 cos theta plus T2 cos phi, and I'm going to divide the right hand side by that term, so I get x by itself. So the denominator here is what was left over on the left hand side, T1 cosine of theta plus T2 cosine of phi. Now, we do know what theta and phi are, and we do know what L is, but we don't know T2 or T1. However, we can use the information that we've got up here in the first equation to rewrite T2 in terms of T1. So if I was to make the substitution from equation 1 that T2 is equal to T1 times the sine of theta divided by the sine of phi. So all I've done here is take T1 sine theta to the right hand side and divide by sine of phi. If I make this substitution into this equation down here, which I call equation 4, then we'll see that x becomes equal to T1 times the sine of theta over the sine of phi times the cosine of phi times L, divided by, on the denominator I still have T1 cosine of theta, and now substituting once again for T2 in terms of T1 sine theta over sine of phi multiplied by cosine of phi. And if I look at this expression here, I notice that T1 is common on the denominator, so I can take T1 out from both terms as a common factor, and in fact I can cancel T1 top and bottom, so the tension force drops out. So everything that I have here on the numerator and the denominator, I know theta, I know phi, I know L. I can put all of those things into my calculator to work out a numerical value for x. And if I go through and do that carefully, I'll find that x is equal to 2.20 meters. Let's quickly just assess that and see if that makes sense. We were told that the length of the rod there was equal to 6.1 meters. So if it was halfway along, it would be 3.05. So certainly it's to the left of that. It's less than that, it's 2.2, so it's the right order of magnitude. We can also easily check the units for this, because the trigonometric functions sine and cosine don't have units. So they're unitless quantities. They're just ratios. So actually sine theta over sine phi times cos phi, that's unitless, so the only units in the numerator is that of length, which is in meters. So on the denominator it's all a unitless number. So the units are consistent as well.